So we're looking at what's going on in the calorimetry lab. I've got some notes over here about the meaning of exothermic and endothermic. And exothermic indicates that something is releasing heat and it's going to have a negative value of Q. Endothermic means heat is absorbed, and that means there's going to be a positive value of Q. So let's talk about what's going on first of all with the metal here. So we'll have a metal. It'll be in a test tube. I'm just going to put little ball bearings here for the metal. It could be any metal. And it's going to have a certain temperature initially, but we're not really worried about that too much, because what we're going to do here is we're going to put it into boiling water. And the temperature of that water is going to be around about 100 degrees Celsius. So what's going to happen here is that eventually the heat will go into this test tube here and heat up the metal, and the metal will have a thermometer in it, and it may get close to 100 degrees, it may not quite get there, but hopefully it should get pretty close to that, and that'll be the initial temperature of the metal, which we'll be able to measure with the thermometer here. Then what we're going to do is we're going to take that metal and we're going to put it into a calorimeter. The calorimeter is going to be a cup. It's going to have water in it, and we're going to know the mass of that water. We also know the mass of the metal as well, of course, because we would have weighed it before putting it into the test tube. And that water is going to have a certain initial temperature. It's going to be close to room temperature, and it's going to be around 22 degrees. Might be more, might be less, but it's going to be something in that realm. Then what we're going to do is we're going to take that metal once it's heated up and stick it into this calorimeter. The calorimeter also has a lid on it as well, but I'm not going to include the lid here because I'm just going to be illustrating what's going on. So the metal will end up, of course, on the bottom of the calorimeter, and the temperature of the water is going to actually end up going up. And the reason, of course, is because the metal temperature is going to go down. That's going to reach T final. And that T final is going to be higher than 22 degrees, but probably going to be not that much higher, maybe about, say, 25 degrees Celsius. The temperature of the water is going to go up, but not by as much as the temperature of the metal is going to go down. The important point about this T final, though, is it's not just for the water, it's also for the metal, because what happens is that the metal will cool down to the same temperature as the water will heat up to. So we call that the equilibrium point, which is going to be different from either of these initial temperatures here. So I'm going to make that the T initial over here on the metal will be about 100 degrees. So you can see that the metal goes down by about, say, 75 degrees. Not exactly that. It's going to vary from metal to metal. And the water only goes up by about 3 degrees. Now the difference here is due to the fact that water has a much higher heat capacity than metal does. Water has a heat capacity of around 4.184 joules per gram per degree Celsius. The metal is going to be probably under 1 joule per gram per degree Celsius. Now to do the calculations here, what we're going to do is we're going to do Q metal. And sorry, we'll do Q water first. Sorry about that. Q water, which is going to be the mass of the water times the heat capacity of the water times the change in temperature of the water. Now the mass of the water we already know because we would have weighed it inside the calorimeter. And we already know the heat capacity of the water, and we also know the temperature change that the water underwent as well. So the Q of the water is going to be the mass of the water times 4.184 joules per gram per degree Celsius times the temperature change, which is going to be the T final minus the T initial. So you can see that is going to be around about 3.0 degrees Celsius, we'll say about that. It's going to vary, of course. And this is going to result in a positive value of Q, which is because the water absorbed heat. It went up in temperature, we know that. So we know it absorbed heat, so it's a positive value of Q. The Q of the metal is actually going to be the negative of the QW. So what I'm saying there here is that the heat released by the metal is going to be the same as the heat released, heat absorbed by the water. So the temperature change for the metal is going to be one where it goes down in temperature and releases heat, whereas the water went up in temperature because it absorbed heat. So what we're going to do for the metal now, we know that Qm, which is actually negative QW, the negative value of QW, is going to be the mass of the metal times the C of the metal, and that's what we're looking for here, is actually that C of the metal, and the delta T of the metal. So that's going to be the mass of the metal, which we already know. For C of the metal is what we're looking for, and this will be T final minus T initial again. And you'll see that the final temperature is going to be around about 25 degrees. The initial temperature was around about 100 degrees. So you see that'll be around about negative 75 degrees Celsius for that. And you can see that this will be a negative value, that'll be a negative value, they'll end up cancelling out. We'll end up with a positive value for the heat capacity, which is always what we should have for a heat capacity anyway, is a positive value. So that will allow us to then calculate this C value we have here, because we have the Q value, which is going to be the same as the Q value for the water, just with a different sign. We have the change in temperature of the metal, which is going to be about 25 degrees Celsius minus about 100 degrees Celsius. And then that allows us to calculate the heat capacity of the metal. So what we're interested in here is figuring out what happens when we add a solid to water. So there's two possible cases that we can end up with here. So we can have a cup that's going to have some water in it, and we're going to add some solid to it. So let's say the initial temperature of the water was, say, around 22 degrees. And then we add solid to it, and let's say the temperature goes up to 24 degrees Celsius, or the temperature goes down to, say, 20 degrees Celsius. So you can see what effect the solid has had here. If the temperature goes up, so T increases, that means that Q solution is going to be a positive value, and what would happen is the Q of reaction is actually going to be a negative value. So when we talk about reaction or Q of reaction, it's always from the point of view of the solid. So it's what the solid is doing. And that's really important, because if you see that the Q reaction, the temperature of the water has gone up, that means that heat must have been released by the solid, which means that the solid's going to have a negative Q value, and that's what I've got up here. That's what's important. Now the temperature going down then, the Q of solution is going to be a negative value, but the Q of reaction is going to be positive, and that's because what happened was that the solid actually absorbed heat, and that's what I've got up here. A positive Q value is from the solid absorbing the heat. But the Q reaction is always from the point of view of the solid, and I think that's what you've got to remember. Now to get the Q of solution, which is really the same as the Q for the water, That's going to be the mass of the
solution
times the C of the water times the change in temperature of the water, which is going to be T final minus T initial. So in the top case, you can see that we go from the final was 24 degrees Celsius and the initial was 22 degrees Celsius. And you can see that that's going to end up being a positive value, which is why Q solution is going to be positive. But the Q of reaction, that's from the point of view of the solid. The solid released heat, which is why it has a negative value. And that's what I want you to keep your eye on here. If we're looking at the other case, 20 minus 22, that's going to result in a negative value, which means that Q solid is going to end up being positive in this case. So here, I'll just summarize that. The Q of the solid, or the Q of reaction, is going to be a negative value. And here the Q of reaction is going to be a positive value. Alright, what we're interested in here is the heat of reaction. Let's see what we're doing with this one. We've got two things. We've got H plus and OH minus, and that's going to give water. And as such, the stoichiometry is 1 is to 1 is to 1. That's going to be important a bit later on when we're looking at this. So let's see what the situation is initially. We have two graduated cylinders. One has HCl and one has NaOH. The Cl and the Na we're not really interested in. Those are spectator ions, to be Cl minus Na plus. We're only interested in the H plus and the OH minus here. Now, these are going to have certain initial temperatures. They're going to be pretty much the same. The initial temperature of each is probably going to be pretty close to around about 22 degrees. Then what we're going to do is we're going to put that into a calorimeter, both of them, and we're going to find that the temperature is going to go up. So the temperature might go up to, say, let's say 30 degrees. It may or may not be 30. I'm just using that as an example. But the initial temperature is going to be 22. The final is going to be 30. So we know that this is going to be an exothermic process, which means we expect Q reaction, which is also the heat of reaction, or delta H of reactions, another way of looking at it, is going to be a negative value. We expect that because we know that heat was released by the reaction, so we expect it to be a negative value. What we're going to do is look at the Q of the water here, which is going to be a positive value, and I know that the Q of reaction is going to be opposite of that. You can look at the previous part of this, the enthalpy of solution, to get an explanation of the signs here. But the Q of the water is going to be the mass of the water times the C of the water multiplied by the change in temperature of the water. And the change in temperature is going to be T final minus T initial. And it's going to be about 30 degrees Celsius minus about 22 degrees Celsius to get that. Now the mass, we're going to have to use the density of the solution here. The density of the solution is around about 1.02 grams per mil, and I think that's in the data sheet. I think you'll find that information. So you'll have to get the mass by taking the density and multiplying it by the volume of solution. Now, if this, let's say this was 25 mils and 25 mils, then the total volume of the solution is going to be 50 mils. That's what's going to go in here. So the mass being the density times the volume means we've got the density and we've also got the volume as well. So that allows us to pick up the mass of the water here, or the mass of the liquid. We're assuming here that the heat capacity is going to be the heat capacity of just the water. That's what we're interested in. And then we see the change in the temperature of the water. We can get that from the differences that we noted here, the T initial and the T final. We know that the Q of the reaction is going to be the negative of the Q of the water. And we know that the heat was absorbed by the water, which is why it has a positive value, but the Q to reaction is going to be a negative of that, because we know that the reactants here, the H plus and the OH minus, actually ended up releasing heat into the water. So that's why we get a negative value here for the Q of reaction. The other important point is that we want to be able to get a molar heat of reaction, or delta H, which is going to be in kilojoules per mole. So what we're going to do is we're going to end up with this Q water, which is actually going to be in joules. In order to get the delta H of reaction, which we want in kilojoules per mole, we're going to need a couple of things. We're going to need to take the joules and convert that into kilojoules, and the joules times 1 kilojoule over 1,000 joules will do that. We'll convert it into kilojoules. But we also need the number of moles here as well. Now to get that, I'm just going to clear out some of this stuff that we have over here. And what we're going to be doing here to get the moles is if we have a certain molarity. So let's say that the molarity of the H plus is, we'll make it 0.50 molar. This may or may not be the molarity you're using in your lab. Whatever it is, you can just adjust it from here. And if you want the moles of H plus, then that's going to be 0.50 moles per litre. Remember that big M is moles per litre, multiplied by the volume you used of the H plus, and that has to be in litres as well. So that'll give you the moles. Remember, what we're interested in though is the kilojoules per 1 mole, and that's what I was talking about earlier with this stoichiometry over here. We're interested in how much energy was released to produce 1 mole of H2O, which means that we're going to have pretty much, because we're going to be using the same molarity for the OH minus as well, and the same volume, then the number of moles should be the same for both of those. But it's going to be a 1:1 reaction. It'll be whatever moles of H plus we get here will equal the number of moles of water that we're going to have here. But it'll be a 1:1 process. After you've gotten that, that will tell you how many moles of water will end up being produced.